Adrian is getting inventive. What's the next one? The more primitive edition.
You know, when inspiration strikes.
Okay, sure, makes sense.
No, so made it Tina?
No, yeah, there's two things inside.
So conspiracy going on? Is there a conspiracy going on?
Yeah.
So it's not no longer loose.
Just waiting for
That
it.
was the reason.
You see in there?
Yeah,
Yeah, so what it does is that it can get over your knuckle because
you can turn it.
you can kind of like finagle it, but it holds it a little bit more so it doesn't spin so much. And then it also kind of keeps it.
Does it? Does it bother you?
Mostly because underneath it doesn't, it just barely kind of touches, but it's enough to kind of like keep it under control.
Steve shows up? Steve knows. Steve, does he know?
He's not interested.
He can watch the video afterwards. Even if he's the one who actually wanted for the seminar to happen. Great.
Good to go.
Thank you, Brent.
For some reason, they removed the tape. I think Karen has to do
No,
that.
I'm
So
not
kind
going
of
to
don't
run
go
too far.
past about right here.
Yeah, I know.
So cool. But it's all ready to go whenever you're ready.
Okay, thank you.
You're welcome.
Hey, Mama. We're waiting for Jenny and then we can start.
How are you?
No, English.
Right. Change the icon.
We're still a bit early, right?
Yeah, no, we have plenty of time. I texted Steve, so
1 minute 20 seconds is plenty.
No, beat that. Just have 2 minutes, couple of minutes.
so could you have that meeting today?
Would you mind closing the door? Thank you. It's okay. Let's start. So let me just say at the beginning, I have no idea how that will go today because I have no idea what will happen. I was trying to play around with things this morning and everything broke. So as it turns out, we really have to do some serious fixing on the FISR end of things, and I'm aware of that. So if things go wrong today, just ignore that and assume it does what it's supposed to do. Okay, but anyway, all of you guys have been bugging me saying that, hey, please explain what is actually primitive and how does it work. And what are the things we have to watch out for when writing one. Most of you have created a primitive or two, or even three. And my assumption always was, hey, if somebody just creates one, then everything is clear. But apparently not everything is so clear, and not everything is well understood, or well enough understood for you to just charge ahead and start doing things with it. So the idea I want to, of the seminar today, is to go back and to show some of the underpinnings of what primitives actually do, what are the arguments for the primitives, how is all that stuff working. And I very much hope that you have some questions to guide that discussion as much as possible. Okay, Phylanx, the primitive edition. Just quickly, great. Okay, so if you remember, whenever we talk about Phylanx, I usually have that A plus B example, right? Sorry, that doesn't work. And what I usually do is I kind of represent that as a tree structure. We have 3 nodes plus A and B. And while I assume that this is enough in terms of explanation of what that means, because this is actually what's happening in memory, it doesn't seem to be quite clear how is that, what do I mean by that when we build this kind of tree data structure in memory. That's one thing I want to go into today. The other thing I would like to discuss is when we have built such a tree or such a data structure in memory, how is it evaluated? How can we extract the result from looking at the evaluation of such a tree if A is 1 and B is 2? Why do we get 3 as a result, and what are the mechanics behind it? Actually, I would like to start a bit with the second one and then go to the first question, because I believe in order to understand that a bit better, we first have to talk about some data structures which are involved when evaluation in Phylanx is actually happening. Well, in the simplest case, what B does when I want to evaluate B or A, in the simplest case it will return a single double, right? Just for arithmetics. But in Phylanx, the thing that can be returned from the evaluation of a single node in a tree, and we will see that a single node in a tree is essentially what is a primitive in implementation. So what a single primitive can return when being evaluated is not just double. But in Phylanx we have a more complex data structure. We want to be able to represent different things. We want to be able to return different things from the evaluation of a primitive. And I want to go through that in a bit more detail with you. So the data type that is actually returned from evaluation from the evaluation of a primitive is called primitive argument type. And the reason why it's called argument type is that it's not only returned from a primitive evaluation, but also passed as one of the arguments, possible arguments to the evaluation. So we could come up with any other name. So if somebody has a better name, we always can change that. But in general, the primitive argument type data structure in Phylanx is the one representing either arguments or results of evaluation. What can a primitive argument type be? Well, in principle, a primitive argument type is a instance of a std variant. Who does know what a standard variant is?
Knows?
Who knows what a standard variant is? Who knows it? Okay. Bambo, you never heard about a variant? You have never heard about a variant either, right? Okay. So let's quickly go into that. And if more questions or more answers are needed, just let me know, okay? If we all know that C++ or the standard library has these various data structures like standard vector and standard map and standard list and so on, then those are containers. And those containers are data structures that can hold one or more elements of the same data type. We all have come across a data type that is called tuple. The tuple in standard C++ in a library is essentially a container that can hold one or more elements of different data types, where each of the elements has its own type, right? It can be a tuple of int, string, double, right? Then you have a container that can hold an integer, a string, and a double at the same time. Now, standard variant is a container that can hold one of a set of data types. So you can say std variant of int, string, or double is something that can either hold an int, or a string, or a double. So it's kind of a type-safe union. If you have heard of union in C, which is kind of a very low-level data structure, a std variant is a type-safe version of that. Because when you store an int in a variant, it will throw an exception if I try to extract a string from it. So you always have to extract the same type that is currently stored in the variant. In other words, it's a means of letting a primitive return either a double or a vector or a matrix or other things through the same data type. Std variant of a list of things. And the list of things is the following. So you can think of a primitive argument type as a std variant of either a node data and I call it bool here. I will say a word about that bool in a second. Or a node data, and I will say a word about node data in a second as well. Double, it can be a string, std string. It can be a int 64t, so a signed 64-bit integer. It can be a primitive, and I will say a word about primitive in a second. It can be a vector of AST expressions. And I explained that in a second. Or it could be a range. And last possibility, it could be nil. And nil is just a empty struct we use as a placeholder to say, hey, it doesn't return anything. Okay? So nil is easy. It's really just an empty struct. Nothing in it, plain. Range is another variant that has been introduced just recently. And range can be three things. It can be an integer range, essentially a tuple of start, stop, step, three integers. And that is used for integer loops. Loop over from 0 to 10 with step 2, something like that. So it represents a range of integers that are evenly spaced, starting with a start value, ending with an end value, and a given step. This is mainly used in Python very often. If you have written Python code, you probably have written for I in range from 1 to 10, do something. Then I will iterate over the integer range from I to 10, and you can do things with it. A range can also be, in Phylanx, can also be a vector of primitive argument types. primitive argument types. So it's kind of self-recursive, right? A primitive argument type can be a vector of primitive argument types. So it can be essentially a list of things. Each of those things can be one of those things again. So you can create recursive, self-recursive lists of things. And the third way, the third possibility of a range, it could be a pair of iterators into a vector of primitive argument types. So it could be just two iterators pointing to some vector of primitive argument types that's living somewhere else, or into a subsection of a vector of primitive argument types somewhere else. And these three things are all ranges because they are all iterable. So when we start iterating them, that one will iterate integers from start to stop, that one will iterate over all elements of that vector, and that one will iterate over all elements in between those two iterators, whatever's in between those. And those iterators essentially are iterators that can point into either a sub-range of the integers or a sub-range of that thing. It's some kind of self-recursive range again. And please ask questions whenever you have fun. Range is okay. Vector of AST expression. AST expression is essentially just our internal data structure that holds a single abstract syntax tree we got from compiling Phylanx, FISL code. And we can store a vector of those. That allows us to store whole programs, FISL programs, where each of the functions is one of those AST blobs stored in that vector. That also means theoretically one of our primitives could return a piece of FISL code to another primitive which is doing things with it, because it's just one of the possible options what a primitive can produce. Well, the primitive. Primitive is if the AST expression is the AST, then primitive is a representation of a compiled AST, namely the representation of another tree. You can think of a primitive as a reference to a root of an arbitrary execution tree. Remember, right? We have three stages in Phylanx. Front end that produces an AST. The middleware takes the AST, does something with it, and produces an execution tree, that guy. And the back end is evaluating the execution tree. So the data structure that can be produced, or the thing that can be produced from any of the primitives, can be either an AST or an execution tree. So depending on what you want to do. Okay? Does it make sense? Please ask questions. I don't want to leave behind any problems, because things might just get complicated otherwise.
Why would we need the AST expression within the execution tree? You can translate all the time to an execution tree and then use that. Why would we still
You could do that, but think about the following. As I said, that data structure is used for return values, but it's used for arguments as well. Okay? And if you want to evaluate a function and you don't know that function up front, let's say you have some code or some tree that is able to evaluate other trees.
Is it like a function pointer?
You can think of it as a pointer to a execution tree. So you can hand an execution tree to another execution tree and let it evaluate it. That's very important when you think about functional programming, right? Map is a function, as a FISL function, is essentially this, is one of those. And one of the arguments is a reference to another function. Right? You give it the body of a loop or something. And that body of the loop can be an arbitrary complex execution tree. But you want to give it to a primitive as an argument. So it has to be in that data structure, right? So you have to be able to pass that along.
So that get compiled again?
Hmm?
It gets compiled to execution tree?
No, that is already compiled.
No, I'm talking about the vector of AST expression.
Ah, okay, that one. That one is more of a convenience thing, which is used in the FISL interpreter. Because what the FISL interpreter does, it looks at all the arguments you specify on the command line. It compiles those as ASTs and hands that thing to evaluation. So think about that as either as a convenience or as additional things. That's not absolutely necessary. We have it just in there because it proved to be very convenient and useful. But the primitive is very important, obviously, right? Does it make sense?
Yeah, I was going to ask, why is it not an AST expression and a vector of AST expression? But okay, that makes sense, because there's only one use case for it.
Currently, we have just one use case. It's an interpreter, essentially, where that comes from, right? There are other use cases, but we can talk about that later. Okay, int64 is easy, right? Because we want to be able to return and pass in integers. Std string is easy because we want to be able to deal with strings. Node data. Node data is an interesting one. Node data is another variant that can be 5 different things. So node data T can actually be a T. It's a variant T. Obviously, right? We want to pass along doubles. It can be a Blaze dynamic vector. T. So we want to be able to represent one-dimensional data structures. And as it's fairly easy to guess, it can be a dynamic matrix as well. Dynamic matrix of T. So node data can be essentially 0, 1, or 2-dimensional thing of type T. And we use that for all arithmetic operations. We also, and that's a node data double, right? I said it can be node data double. This is for arithmetics. The other thing is node data bool, and actually we don't have a node data bool there, but we store it as a node data uint8, which is actually the same thing. It's just a byte. We just don't use bool there because of some idiosyncrasies in the implementation that are not important to this discussion here, but we can discuss that offline. So just whenever you see uint8 in the Phylanx code, think bool, and you're always right. And this node data bool is used for the comparison primitives, right? Compared to matrices element-wise, and you get a matrix of bools where each element of the resulting matrix gives you the relationship between the corresponding two elements of the matrices you compared, right? A less than B, you get a Boolean matrix of true/false depending on whether the elements are less or not of the two matrices. And those results are stored in the node data bool inside the primitive argument type. But I said that node data can be 5 things, not 3. What else do we have there? We also have the ability to store a Blaze custom vector T and a Blaze custom matrix T. And I hope by now that you all know what a custom matrix is. Just for those who don't, the difference between a dynamic matrix and a custom matrix is that a dynamic matrix allocates the memory. A custom matrix just refers to another dynamic matrix somewhere else. So it doesn't own the data, whereas the dynamic matrix owns the data. It's the only difference. Otherwise, both are matrices, both can be used for all operations. It's really just a means of avoiding additional copies, because instead of copying the matrix, we can create a custom matrix that refers to the original one and hand that thing around, which is a cheap operation because it's essentially just a pointer to the other thing. Okay?
Why don't we use the uint as a node data and we have a separate uint 64?
We have node data double and node data uint 8.
Yeah.
Why don't we have a node data
uint
uint 64? Because nobody has asked for it.
So why do we have a separate one, independent?
When we started off, we had a bool, a node data double, and an int. Shahrzad went through the lengths and replaced the boolean with a node data bool or node data uint. And if somebody needs a matrix of integers, you will have to go through the code and change all occurrences of int64 by node data int64. So whenever we need matrices of integers, which we didn't need at this point, we can easily change that.
Wouldn't that be a problem with the size of the variance?
No, all node data is, you don't think that?
Adding another node to current development type.
Well, a variant is either that, or that, or that, or that, or that. So the size of the variant is the memory required to store that variant is equal to the memory requirements of the largest of the types in there. So adding another one will not change the memory requirements of the variant. What you're referring to is the adding yet another type there, right?
Yes.
But we would replace the integer 64, we would throw that out, so we still would have 8. But in the future, we might have to go further and might have to create more options in node in the variant. Let's see how that goes. Okay.
Can we have a variant of vector type?
Hmm?
Can we have a variant of vector type?
Well, we have a variant of vector. What do you
Oh
mean?
yeah, so you're right. So why don't we have everything as a node data? That's what I don't get. So
Well, the node data is kind of the numeric type. So when you read node data, just read numeric or whatever. So it's a 0D, 1D, or 2D, and in the future perhaps a 5D representation of some numeric entity. So it's more than matrix type in some sense. Whereas the others are non-matrix types. Yeah, kind of. Conceptually different. But
the name for me, I don't understand.
yeah, you know, we can change that.
No, I'm just trying. I thought I'm missing. I was missing something.
No. The name node data came from the initial idea where we only had the numeric types, and there it was the data that was handed around between the nodes. So that's why it's called node data. But we can do bike shedding all day long and find better names for things, and I really don't care. I'm not attached to any of those names. I'm aware that they are, well, flaky at best. Okay? So that's what we have today. If you want to improve that, by all means, let's change things. It's really the current state of affairs. And I think it's important to understand that we have these data structures because all the code is kind of revolving around these central data types. Okay?
One more question. So if I remember correctly, node data is the only thing in the IR, right?
Range is an IR as well.
Range is IR. So why we have IR as a separate thing? I don't get it.
Change it.
No, I'm just not.
There's no reason for it. It's just how it happened.
So everything is kind of part of the.
Everything's kind
It's
of part of the
execution
whole
tree.
thing. Yeah, everything is kind of part of the. I can't explain these things. So things just ended up in different namespaces for reasons we can.
I'm just
If
trying
it
to.
turns out to be non-consistent, these things can be changed. So, okay. So don't get fooled by naming. Naming is really just completely superficial. But currently we have range and node data in a different namespace from everything else, which is kind of not quite what we want. The other note I want to make is that we most of the time don't actually use std variant because std variant is a C++17 library feature, and since we don't rely on C++17 but only on C++14, std variant is only used when it's available. Otherwise, we use an implementation that is providing the same functionality. It's in a different namespace. It's in mparc variant. So if you see in the debugger something with mparc variant, this is just implementation of a std variant interface. Okay? And that's because std variant is not available on all platforms today yet. But functionally, these two things are completely equivalent. And we pull them into our util namespace. So it's all called Phylanx util variant. And that maps to either that or that, depending on what platform or what architecture we are. Okay, more questions so far. Good. So let's do some coding. Explained things long enough. What I would like to show you is how these trees are being built. What does it mean to create that execution tree? How is it built in C++? Just for you to understand that this is no magic going on. It's really essentially straight C++. It just seems to be a bit complex because so many things are going on around it that it's difficult to see the gist of it. And for that, what I really would like to do is just to create a very simple execution tree for a simple add operation. Let's assume we have two different types of primitives. One is called variable, and that thing can hold a single double. Right? A and B would be variables holding single doubles. And we have a primitive that is called add, and that thing will add values. Okay? So let's start with that. So as I said, let's start with a variable, and as I said, it will hold one double. And it has one constructor, variable that is initialized with a single double. And what we also need is a means of evaluating its current value. We want to ask the variable, what value do you store? And we do that by, in the simplest case, by calling a function eval that for the variable just returns our value. Okay? And now when we want to create a variable, and please bear with me, for about 5 minutes I will use pointers. It's really just for simplicity. We will get rid of that, and I will not care for these 5 minutes about memory leaks and those things, just for semantics, to give you an idea how the bare one is implemented. So let's say variable 1, or call it left-hand side, is a new variable, and we initialize it from 42. Okay? And we have another variable, and we call it right-hand side, and we initialize that from 2. And what we are now able to do is to say, hey, just please, variable, show me your name, your value, by calling eval. Standard end line. And we can do the same thing with a right-hand side variable, right? So it should print 42 and 2. Let's see if that works. Yeah, 42 and 2, as expected. No magic there. Okay, now let's create that add primitive. That data structure that knows how to add things. And we call it add. And add has a constructor which takes two variables in a simple case. Left-hand side variable, right-hand side, and we will store two of those as members. Let's call it left and right. So we initialize left from the left-hand side and right from the right-hand side. And what we obviously also need is a evaluation function, right? We want to evaluate, we want to ask the add primitive, hey, what's your value? So what needs add do in order to return the value? What would you do? How would you implement eval for the add primitive?
You add the two return the
Well, sure, you just do return left eval plus right eval, right? And now we can actually create one of those. We can say add pointer op equals new add left hand side, right hand side, and we can print the value. Okay. So it should print 42, 2, and 44. I hope so at least. Let's see. Yeah, everything's okay. So essentially what we have done, if you think of it, we have created an execution tree with 3 nodes. An add node, that one, and that add node has 2 pointers to the 2 leaf nodes, A and B, which is 42 and 2 in our case, right? If you understand this, you understand how execution trees and Phylanx work, because it's nothing else. Nothing else. Well, Sun's not working with pointers, but with HPX components and other abstractions on top of it. But essentially, that's it. So whenever we evaluate or whenever we have a Phylanx expression, and we compile it using an APA function, which is actually called compile or something, if I remember correctly, then the Phylanx is translated into an AST. An AST is another data structure, and then we give that AST to a compiler, and the compiler gives us the tree that corresponds to our AST, that corresponds to our Phylanx. So whenever we have Phylanx 1 plus 2, the compiler actually creates a execution tree plus 1, 2 from it, and gives us back the pointer to the root of that tree. End of story. When we then evaluate that tree, what we do is we call eval on the root, and that trickles down and calls eval on the next one, calls eval on the next one, and so on, until the values are gathered back and the resulting values return to the caller. That's all what happens there. Okay? Does it make sense? Oh, great, then we can stop talking. You sure that this is clear? Okay? I'm not going to get rid of the pointers here. It's really just for exposition so that you see it. And I'm aware that there are 3 memory leaks and other bad things happening here. Let's not worry about that. It's really for you to understand things. Well, one thing I want to add is that in Phylanx, the stuff is actually, well, let me put it that way. If you look at these 2 primitives, you see that the eval function is actually equivalent for both. And that currently the evaluation down here is aware that we are dealing with an add primitive and with variables. So this wouldn't allow us to combine add primitives. We couldn't say A plus B plus C by just having A plus B and C. We couldn't create larger trees of it because, well, add expects to pass into variables. We can't pass another add into an add, right, to cascade things. And in order to fix that, what we can do, we create a base class, which let's call it primitive. And that base class has a virtual function, double, and doesn't implement that virtual function. and we derive our variable and the add from a primitive. Now we can initialize add from two primitives, store two primitives here. And what we can do here is make it completely agnostic of the type of the things we deal with, right? So this evaluation here is not aware that op is actually an add operation. From a standpoint of the code, evaluating is op as a generic primitive. It can be anything. Like these things, it can be anything. And now we can combine add operations, because we could just do the following. Let's create a new add, but this time we call it op1. Now we, let's leave it that way. So we create a larger tree consisting out of an add primitive, which has the right-hand side, which is 2, and on the left-hand side it has another add primitive, which has 42 and 2. So I'd expect this to print 46, right? Okay, let's see if that works. So in other words, by deriving all primitives from the same base class with a virtual function and implementing that virtual function in the derived classes, we completely abstract away that we have different types of primitives from the standpoint of the evaluation of the tree, right? And that's what's done in Phylanx as well. And that's why all Phylanx primitives are derived from a primitive base type, which essentially is just a virtual function definition for the evaluation function inside the primitive. And the evaluation happens through the base class and the virtual function call mechanism. And you certainly have to understand what a virtual function is. I hope you do. You might not see what a virtual function is yet. Let's talk about that separately. Okay? Essentially, a virtual function means that all I have is a pointer to the base class, but it still calls a function in the derived class, no matter what it is. And the compiler doesn't have to know at compile time what the derived type actually is. It can be combined at runtime and composed at runtime. Okay? So whenever I talk about, or we talk about execution tree, what we mean is the pointer to the base, to the root of a data structure that is composed out of pointers, and that, when evaluated, gives us a result we want to get. Adrian.
Can you reiterate the connections between the execution tree, the AST, and
Okay.
the...
Good. I understand where you're coming from. This is focusing really on the execution tree part, right? So how do we get from the AST to the execution tree? And you can think of the AST as an internal representation of PhySL. If PhySL, you write 1 plus 2, it's a string representation. That thing gets translated into an internal data type that encodes 1 plus 2. I don't know if you remember in the presentation I showed during the project meeting, on one of the slides that I was talking about these Russian dolls. It's a data structure which is a Russian doll, where you can kind of compose things out and you still have an AST afterwards. So whatever you do, how complex that thing gets, it gets larger and larger and larger, but it still stays an AST in terms of C++ type. It's all the same type. So I can hand around that thing, and it kind of internally gets larger and larger and can express larger and larger expressions. And that allows us to represent essentially any PhySL expression, how complex it might be, as one C++ internal representation that corresponds in structure to the thing we wrote. And that is the AST. That translation is done by a parser. We can look at that code, and that parser is essentially just a description of the PhySL structure of the language. in the end we get, as I said, a C++ data structure, which is a AST expression, and we call it AST expression. And I think in the very first lecture when we talked about things, I already showed you these AST expressions. Let me pull that up again. So here is the data type AST expression. It has a bunch of constructors. Let's ignore those. The important thing to know is that an AST expression contains out of two pieces. A of an operand, which is another type. I'll show you in a second. An operand, which is called first, which is the most leftmost thing in an expression, and a vector of operations, which is the rest. And an operation is a plus or any operand with another one of the mathematical operations, plus, minus, division, multiply, followed by another operand. So an expression can be a plus b plus c plus d times 8 or something. And a will be first, and the rest is encoded in the vector. And each element in the vector is one of those math operation plus another operand thing. Okay? Does that make sense? Trust it? You're kind of... Okay. So let's look at an operand. An operand is a data structure. Let's ignore the constructors again, which is, here we go, 1 second, which is a variant that contains out of nil, can be nothing, or a primary expression or a unary expression. Let's ignore the recursive wrapper, that's an implementation detail. So an operand can be either nothing or a primary expression or a unary expression. So let's see what a unary expression is. A unary expression is an op token, which is plus minus something something, followed by another operand, and so on and so on. So these data structures somehow describe the initial expression we had, just by building blocks out of it. And the topmost level block of that is AST expression. That represents the whole thing. Okay? So in the end, as I said, this is just a means of representing what we have in a string in memory in C++, so that we can look at members, can kind of drill down and open up the Russian dolls until we are at the leaf nodes and we see what's actually going on. Okay? Now, this is the first translation step. The next translation step is when we have that AST and we have done some optimizations on it, we have transformed it, or we haven't done anything to it. Then there is another translation step, which we call the compiler. The compiler. And that compiler traverses that AST data structure by looking into members, kind of going down that thing, and produces an equivalent execution tree structure. What it does, it takes the AST, goes to the very leaf of that AST description, and sees, it's a variable. So it instantiates a primitive of type variable. Then it goes one level up and sees, okay, it's a plus. So it instantiates a primitive of type add operation. Then it looks into the other operand of that plus and sees, it's another variable. So it creates another primitive instance variable and passes those two pointers to the add operation at construction time, which gives you the representation of the lowest level add operation in that AST, right? Add AB. And it repeats that process from the bottom up until it gets to the root of the AST, which gives you a execution tree that is equivalent in structure to whatever was described in the AST. Does it make sense? Yes? No? That's it. And once we have the execution tree, we call eval on the topmost node as an eval function. We call that, and that calls into the root. The root is a, let's say, multiply operation. it has 3 operands. So it calls eval for all 3 operands and waits until the results come back. Each of these 3 evaluations end up in different primitives. Each primitive has its own functionality encoded in the eval function, and everybody of you have written at least one of those evaluation functions, right? So for add operation, the evaluation does add. For multiply, it does multiply. For comparison, it does a comparison operation. And before doing the actual operation, it calls eval on its children. And that happens. So, and this way, it kind of first bubbles down to the leaves. And the leaves are probably variables or file inputs or whatever. And they return the whatever they produce to its parent node. And the parent node does its operation and returns its result to the parent node, and so on. And once that process is finished, we have the result of the evaluation of a expression that came from the FISL string in the very beginning. Is that what you were referring to? Does it make sense? Is it a bit more clear what's actually happening? Yeah? Okay. Any questions so far? So what I really suggest is that you look at that file, node HPP.
Would the execution tree be just AST plus more nodes? Will it be reordered? Would it be
Nothing. It would be one-on-one AST. Everything in the AST corresponds to one node in the execution tree. Okay? Well, not quite. I mean,
It has more nodes at least.
that one, look, that is a unary expression, so it can express unary expressions, namely either a minus something or a not something. Right? It's a unary minus applied to something else. So, and these two things would be represented by a unary minus primitive in the execution tree. Because whatever it gets, it just slaps a minus on it and returns the result. And if that op token is actually not, then it's a Boolean operation, and it evaluates its child, and whatever comes back, it slaps the not on it and returns the result. So the AST description is kind of translated in the corresponding set of operations. And that mapping, by the way, between the AST and the execution tree is done by the patterns you have defined in the primitive, and I will get to that in a second. Right? You remember you always have described some mini FISL expression with _1 and _2 and so on in it. And that is a pattern that is used to match subtrees in the AST that correspond to a particular primitive. For instance, the unary primitive with a unary minus primitive is just probably minus _1. And that means whenever you see a minus, a unary minus, with something else in the AST, translate that to a unary minus primitive and initialize it with that something else. So that when it's evaluated, it will evaluate that something else and slap the minus on it and return things from its own evaluation. Okay? Makes kind of sense? And I'm almost done. I know this is kind of tedious. But I think it's important just to talk about that in that explicit way, just to get all the information across. Does that make sense, Rod? You had the most questions about primitives. I mean, makes kind of sense.
Yeah.
Good. Okay. So what I want to do now is just go into the Phylanx project. This is Phylanx, right? So our CMake generated Phylanx. And I go into the arithmetics primitive. And what I want to do, I want to implement a primitive, actually. And that primitive, to make it really simple, can handle only single doubles and will add 2 of them, just for the sake of it, right? There's not much functionality there. And it's a puny part of our add operation, but it will demonstrate what the primitive is actually doing rather nicely. Okay, so I prepared these 2 files, my out operation HPP and the CPP file, currently empty. I just left it in that namespace so we don't have to annotate types, so the types will be found nicely. You can put your primitives in arbitrary namespaces, that is no limitation. It's really just for convenience during that small talk. Okay, so what do we start off with? We want to create a data type. And that data type, let's call it myAdd. Okay? Same way as we did that for that very small example I showed. So we create a new data structure, and we need to derive that from a type that is called primitive component base. Again, don't blame me for names. That is historic. So currently, the base class is not called primitive. The base class is called primitive component base. We might want to rename that because it has nothing. It's not a component anymore in the direct sense. These things need to be default constructible for various reasons. Let's not talk about that at this point. But it needs a constructor that actually takes a vector of primitive argument types. Come on. Okay, so all primitives need a constructor that take, in our example we had these separate arguments, right? We were initializing add with left hand side, right hand side, and the variable was initialized from a double, and other things might have other constructor parameters to make things consistent across all primitives. What we do in Phylanx is that each primitive is initialized from a vector of things. Okay? And these things are interpreted differently by different primitives. And here is our primitive argument type thing I talked in the beginning. So primitives are initialized from primitive argument types. And that means when I create an add primitive, I can initialize it from two literal values, 42 and 2, right? Because I could store 42 and 2 there. But I could initialize it from two other subtrees which I already have created. And those subtrees would be represented by the primitive thing I had in the list of options, where I said, hey, this is just a pointer to another subtree, another execution tree. So I can pass transparently different things and initialize my add from different things, and add can react to different things. Okay? The easiest what we can do, we just, hold on, let's not implement it here in the header file. Let's implement things in the CPP file. And the second thing we really need is, okay, let me add one more thing. Our constructor actually takes two more strings. Two strings. One is the name of the primitive, so it gets told this is your name. This is important for error handling so that we can print the correct name of the primitive for exceptions and stuff. And a second string that represents the file name the original source code was read from. And this is used just for error reporting. So if an error happens, we want to report when you compile things, right, you want to see the file name and the line information, right, where things happened. This is essentially the file name, which will be used for reporting where the original stuff came from. And this is the name of the primitive, which is add or anything else. For the generic one, it's very important because that is actually sine or cosine or whatever. And you use that information to figure out what the generic primitive actually should do, right? If you remember that. Okay, So that's what the constructor is, and all constructors of all primitives have to have the same set of arguments. And this is because the compiler always instantiates a new primitive using the same set of arguments. Whenever it matches something, it instantiates a primitive passing the corresponding arguments in. And the second thing is our evaluation function. Eval. And here things get a bit interesting, and I'll explain that a bit in a second. This is our evaluation function. And all evaluation functions for all primitives have to return a future to its result, where the result can be anything in the primitive argument type again, so it can return anything. And it has to take one additional argument, which is another vector of primitive argument types. And I will not go into that one, because it's a fairly sophisticated use case which is supported by that. For now, let's ignore that argument. Let's assume it's not there, okay? And then it's again our evaluation function we had in our very simple example. Well, the only difference is that it's supposed to return a future. And this has nothing to do with Phylanx. This is a purely HPXy thingy. Because if you evaluate a tree, let's assume you have one operation and you have two very heavyweight operations, add and some big operation here and a big operation here, and you want to calculate the sum of the two results of these heavy operations. What you really would like to do, you would like to be able to evaluate that thing and that thing concurrently. Or that thing on that node over here and that thing on that node over there. So you want to spawn it concurrently. And the way HPX is doing that is by doing async, creating a new thread, and async gives you a future to those operations. And that means that each evaluation of all these subtrees has to return a future to its result. And this is what that future is all about. And that's why we have a future on all levels. So all evaluation functions return a future to the result it will eventually produce. This is a very important thing, because what it gives us essentially, if we have the execution tree, which is a static data structure, right? We have composed that statically. We have passed the pointers in there, and in the end we have a static data structure. Then evaluation generates a corresponding dynamic execution tree that is composed out of future dependencies. Right? It spawns that one, gets a future, does something, returns a future itself, does something, returns a future itself. So we get a dynamic data flow graph that allows us to execute these things. I apologize. Okay, does it make sense? So that's why the future. So now let's quickly implement that. One additional thing we need, and I'll just copy that from the arithmetics, from the add operation, is a function that will be used by the compiler to create one of those guys. Let's call it create my add operation, and let's call it my add. What this thing does, it creates a new instance of that guy by passing a string that represents that guy to Phylanx. So that tells Phylanx, please create a new primitive that has this name. And the arguments are the same as before. The only difference is that there's an additional locality given, so we can create a primitive over there on a different node by specifying a HPX locality. Do it over there, okay? So this is a function we can always essentially copy-paste. The only thing we have to change is that name of the thing, and that thing has to be unique. And that is a thing we will use in PhySL itself when we ever call it. Because when the compiler sees a myAdd, it will use it here to instantiate things. Okay, and now the implementation. And I'll just speed things up. I'll copy things mostly from okay. What I'll copy is the constructor. And that constructor is probably always very, very similar for all primitives. My add. What you usually want to do here is really just forward the arguments you got to the base type. Okay? Okay, this is an RW reference. I have to fix that I messed that up here because I said it has to be const reference. It's actually this way. Okay? And the second thing is our evaluation function. And that one is a bit interesting. My add operation. This is the eval function. So let's implement the evaluation function now, because we have to do something. Now let's assume that we use our add primitive always with, oh, the header file is missing. I will add that in a second. Always with 2 arguments, just for simplicity. So that means that this thing always contains 2 elements, because that is the vector the primitive is initialized from, right? And we know it's only 2 elements, so this is the only thing that can have it. Also, we know that our primitives, that the things represented by those operands have to be numeric, because we want to add them up. Okay? So what we do, we ask those two arguments, please give me your numeric representation. Numeric operand 0, and we have to pass along that argument I ask you not to think about. We have to pass it along. Let's ignore it. What this does, operand is a member of the base class, which stores whatever was passed in the constructor. So when this contains 2 elements, that thing will contain 2 elements again. Okay?
Why we just don't call eval on that one?
Huh?
Why just not call eval on the operand?
Because, very good question, because it can be a literal value, which is a 1, and the 1 doesn't have an eval, because if that thing already has an integer in it, you can't call eval on it. You can call eval on it only when it's a primitive. In all other cases, you already have the value you need. And what numeric operand just does is it looks into its argument. If it's a primitive, it calls eval, and if it's not a primitive, it gives you whatever's in there. So it's a very simple helper function that makes sure that you get a numeric thing of whatever's in here. Okay? So it handles the eval, not eval case for you, depending on what is in the variant currently in there. Okay? So let me add the header file quickly. No, I have that. What's going on? Why is it not happy with
Did
this?
you call it my add operation?
Yeah, sure. I called it. Okay. Right. I called it my add only, right? Okay. Now things should be good. Okay. And we do the same with the right-hand side. But the right-hand side now is the the second element in our numeric operand gives us the value that's in here. If it's a literal value, if it's an integer or a matrix or something, it gives us that directly. But if it's a primitive, it will call eval. And that eval gives us a future. That's why the whole thing returns a future. So these two operations kick off the two operations asynchronously. It evaluates the left one and the right one. If it's already there, it's fine. Otherwise, it will go to the other node, will calculate things, but gives us a future immediately. So these two futures might not be ready when we return from here, right? So we have to do something about it. We can't use those results to add things, actually. So what we do, we use HPX data flow, right? Just to remind you, data flow is a HPX helper function that is initialized with futures and a function. Give me 1 second. Okay, so we pass the two futures to a data flow, and we have a function. What data flow will do, it will wait for those two futures to become ready, and once those futures have become ready, it will call the function, and will pass the futures into the function. So this function will have two arguments. Both of them are futures. No, that's wrong. I lied. That is actually a node data double. Because we know numeric operand already knows that we want to have a node data. So this function will be called with future left-hand side, future right-hand side. Okay? Once these two futures have become ready, Dataflow invokes that function and passes the futures to the function. That's all it does. So at that point, inside the function, we know that these two futures have become ready, otherwise the function wouldn't be executed. So all what's left is we have to return our result. And since we know that left-hand side, right-hand side refer to scalars, because we said we want to use it with scalars only, all we have to do is to first tell it that our return value will be a primitive argument type. And we have to return whatever our evaluation is, which is left-hand side dot scalar plus right-hand side dot scalar.
Don't you have to do dot get on it first?
I have to do dot get. Left-hand side dot get dot scalar. Right. Okay. So we extract the values out of the futures, call scalar on it because we know it's a 0D data structure. We get the double value, add things up, and return our value from here, which will make the future returned by Dataflow ready, which will trigger the next operation one level up. Okay? So let's see if that actually compiles what I did here. No. So what did I do?
Horizontal blur.
It's probably operates. Yeah, it's operands. Operands is a member of the base class which stores the values it got initialized from in the constructor. Nothing else. It really just stores those things. Yeah, it compiles now. Okay. That's essentially all what we need for a primitive. We need a constructor which stores things, and we need an eval function which is doing some asynchronous magic to produce a result. There's one thing left, and that is the pattern I mentioned in the beginning, that allows the compiler to look at the AST and to see, okay, the user wants to invoke a function called myAdd with 2 arguments. I have to create a primitive that actually implements that thing, right? And this is done by adding the pattern, which we can just steal from the add primitive again. This is that thing. here, let's add this. That's my add operation. And we have to add that to the header file as well. Just to declare it. And we do several things. This name has to be the same name as used in the header file in that creation function, right? We called it my. And additionally, we have to provide it with a pattern, with at least one pattern. And this is how we want to see things in the PhySL. So whenever PhySL has some my underscore add in it with 2 arguments, and underscore 1, underscore 2 are kind of placeholders representing arbitrary things that are in the AST, then the compiler will instantiate a primitive, our primitive, with whatever 1 and 2 are. Whatever that is, it will create a subtree and pass that subtree to the constructor of our my add primitive. I have to fix one thing, namely, I called that my add primitive here, I believe. That's this other function I just defined in the header file, right? It's here. I call it my add primitive, my add operation here. So this one is my add operation, and this one has to be this way. So these pointers are 2 helper functions that help the compiler to instantiate the right things. That's nothing else. It just tells the compiler, whenever you see this pattern in the PhySL, please call this function. And that function will create the correct primitive, will hand it back, and then the compiler can continue. Yes?
If you actually have the wrong type of value inside of one of the things that you pass it,
That
right?
will throw.
Will it throw at execution?
It-
So it does,
it will
it does at
throw.
runtime.
It will just throw at runtime, and you will get one of those errors. Hey, expect numeric type, but got, I don't know, string or something. Okay? So these things have all the errors, and will throw the errors for you. So when you, and there are many of those operand functions. There are list operand, integer operand, numeric operand, string operand, and so on. And you call the function you need in your concrete use case, because you know, hey, my first argument has to be a string, so I call string operand. My second argument has to be a numeric node data, so I call numeric operand, and so on.
It's basically a concept for what is inside.
Right. It just tells Phylanx, please interpret whatever is in here as a numeric operand,
And
and
if
if
it's
not,
not,
throw. And that guarantees that we have a node data that is valid. Okay, in that case, we didn't check that it's actually 0-dimensional. But that's for us to assume. We can handle that, and all the other primitives handle that. Okay, that's it. Now let's compile things. I'll just build that thing. I hope it will compile. Will take a second. Well, not quite. But okay, let's build it first. What did I screw up? Declaration.
Where else is it declared?
Hmm?
Where else is it declared?
I don't know. Where else is it declared? I have it in here. I don't know where I put it. I'll help you guys. I'm not
Oh, can you
seeing-
go back to the header file? Can you go back to the header file? Match data.
Match data.
Yeah, you can,
Okay, this one.
but you're declaring it here.
No, I'm defining it.
Oh, I'm sorry, yes.
Did I forget the semicolon on the other end?
No.
That's bad. screw up. Redeclaration of member is not allowed.
I'm pretty sure the second time it sees it as redeclaration. Can you comment that?
Do we do here? Let me see. I just copy pasted the wrong thing. Sure, it has to be static. That's it. Okay. Otherwise, it's not IP. Sure. Okay, and what I now have is I have the interpreter somewhere. Okay, it has built things, and I have that test script, which I will run with interpreter. And we will see that it will still fail, and I'll explain why it will fail. Just rebuilds the interpreter, it will take a second. But we have all the pieces in place now, essentially, except for one thing, and I'll explain that, what's missing. So we will get an error that my add is not in a simple table yet, so it doesn't know that. But what we already see is that test.physl is that code name which was passed to the constructor, which is used for the error reporting, and the 2 and the 1 is line 2, column 1, and this information comes from the name because it's encoded in the name which is passed to the constructor, so the primitive can do the error handling, can extract that information, can report it to the user. So the thing missing is the following. We need to tell Phylanx itself that there is a new primitive. And that new primitive, we do that by adding that macro in one of the files. My add operation. So we have to, for each primitive, we need to have one macro.
Should you include it here?
It doesn't matter. Okay. So for each primitive, we have to have one of those macros in our source code somewhere, because that is doing all the groundwork for us to for creating all the types we need for things to be created. And you really don't want to know what's going on there. Oh, that's still not good. I need to build it. So let's rebuild the plugin. And this will actually make it work. You see that is the match data. That is that pattern. And this macro will insert that match data into the compiler's table of things so that the compiler actually will find it and will do the association. Because otherwise the compiler wouldn't know about that particular match pattern we just described. So if I run it now, I should get 3 as a result. Yes. So as you can see, creating a primitive is fairly easy. All we need is a constructor and the eval function, and a slight amount of boilerplate around it to make it work. And that's all what's needed. So I hope that kind of explains a bit of what's going on there and might help you to understand what actually is happening when the code you wrote is executed. Because you might not have seen all the dependencies or all the implications at this point. Okay? Make sense?
Yes.
Good. Then let's wrap up at that point. Thanks, and thank you, Brendan, for recording everything.
And can you send me the code that you
Yeah, I can do it.
lot of that stuff. It's essentially volatile, if you want. Thank you for setting everything up. Ja, ich komme zu noch.
Forget, just override it.
So, we don't properly use features in our primitive logic. We don't really use primitives in our primitive, we don't really.
Do you know what was override do? And I find there was some class blah blah override semicolon.
What does override the keyboard do?
Yeah. In some header file somewhere he defined something and there was override at the end of that definition
I
class.
can't remember what it was.
It was something like at the end of you write equal to 0, make it neutral, but something like that at the end.
Override.
Yeah.
This is the virtual method, that is overriding. It shows that it's a virtual method, that's where you override the virtual method, it says it's an override.
You should define it, we really don't say.
So is it only if you define?
If you have more than one virtual function, then this means that this one overrides another virtual function. That's what it's trying to do. That's what it says.
Yeah, because it's. So it's when you want the base class function to be called?
Oh, so never the base class function is called, right?
Wait, confused, give me a second.
Shows you really have to put this is the virtual method that is overriding the virtual method of the base class. The compiler also knows that it's an override, so it can check that you're not altering any users that you think are overrides. Yeah. I just learned what I should know. Do you remember how much you thought
Yeah, I
about
told you that
numeric?
just ignore it.
That's my problem, I don't know what to ignore. Because for a long time,
That
it's like a
recursive
new-
grammar thing, we spent like
What?
We
The
spent about
yeah, the recursive.
45 minutes trying to understand that.
And we also look into the numeric value, how it works, do you remember?
I used to say that you got it, and you said it's not.
The key is knowing what things you can just.
Yeah, that's the problem, and that's why I
You
learned.
need to like do
Let go.
the Dirichlet method, right? So what he does is he knows what you need to do, and that's it.
How do you know what you need to know? That's what you
Just
should
try
like,
to make it work.
but you should try to make it work properly.
Yes, of course. All of this class and everything.
It's not properly.
Oh.